Oh,
Good evening. Hello, Kiera.
hi, Michael. How are you? Really excited for tonight.
I am very excited. We've got another great distinguished lecture lined up, and it's great to be off and running for the fall term. And welcome to everyone who's already here. And yeah, feel free to drop your where you're logged in the comments section.
Yeah.
Happy to always see that diverse geographical list here.
Absolutely. And we're really excited tonight to kick off the fall season for our Distinguished Lecture Series. Just a reminder that the next one will be October 18th. We will have Carla Cotright Williams joining us, and she'll be talking about mathematics and policy. So be sure to mark that date on your calendars.
Absolutely. Uh, I wish there was time to do everything. This community of people who's willing to share their thoughts, their expertise, their wisdom. It's really a rich. We live in a great community. We're part of a great community.
Agreed. Agreed. Really excited for tonight. So,
So,
yeah,
do we want to go ahead and introduce our speaker for tonight?
let's do it. Let's.
All right. Oh, she got cut off very quick. Federico, welcome, and thank you again for joining us for tonight's lecture. We're all looking forward to it. I will start by noting that you have been speaking for some time in through various forums about your enthusiasm both for mathematics and for developing the community of mathematics and connecting those two through your work. So I love that and I appreciate it. I'll just say to the audience, if you want to get some more insight into that, there's a great interview in a recent issue of the AMS Notices, an interview with Federico in the early career section of the AMS Notices. So I encourage you to read that. It's a great thing. So again, thank you for being with us. Um, Anything you want to say before I do the formal intro?
No, I'm just excited to see Oakland in the house, to see Bogota, to see Barbados. So yeah, I would love to know a little bit more about who's here. So please let us know where you're tuning in from. And yeah, no, thanks so much for having me. It's a really wonderful opportunity to get to speak to people about things that we love. So it's
Ah,
a it's a great honor to be here.
and I'm seeing we've got somebody from Bogota.
Yeah,
All right, Oakland. So we're getting there.
yeah.
All right. Well, let me kick off the formal introduction. Um, Federico Ardila-Mantilla earned his PhD from MIT in 2003 and has been a professor of mathematics at San Francisco State University since 2005. He's won the National Science Foundation's Career Award for Research, the MAA's Heimel Award for Teaching, and the AMS's Mathematics Program That Make a Difference Award for Service. That's a pretty well-rounded collection of things. So I think that speaks volumes right there. Federico is a fellow of the American Mathematical Society, the AMS, as well as the Columbian Academy of Science, and was an invited speaker at the 2022 International Congress of Mathematicians. In his research, Federico investigates objects in algebra, geometry, topology, and applications by understanding their underlying combinatorial structure. Federico loves working with and learning from students. He has advised 50 thesis students. He founded the San Francisco State Columbia Combinatorics Initiative, which is an international research and educational collaboration that also hosts more than 200 free hours of combinatorics lectures on YouTube. So I encourage you guys to look for that. I think that's fantastic, that international collaboration as well. Federico also co-directs MSRI Up in Berkeley, a summer research program designed to increase the participation of minoritized racial groups in mathematics. Outside of mathematics, Federico DJs with Colectivo La Palenga and plays Afro-Colombian marimba music with Neblinas del Pacifico. I couldn't help but notice, Federico, the albums behind you. I'm glad to be here with a fellow vinyl enthusiast. We can keep the turntable industry alive for a little bit longer. So, and again, tonight's talk, Hidden Patterns, the Shape of Multiplication. I love starting with something that seems like, oh yeah, we all know multiplication. And pretty soon we learn that there's more to learn. So Federico, thank you so much. Looking forward to your talk. Appreciate it very much.
Okay, thank you. Thank you so much, Michael. Thank you for such a lovely introduction, and thank you all for having me. It's one of the wonderful, unexpected benefits of these days is to be able to talk to people all over the world about the things that I love. It's wonderful to see some familiar names and some new names. Let me say that I am able to see the comments as you are writing them, so feel free to participate, to jump in. So yeah, let's get started. So I would like to tell you about some patterns within the multiplication table. So as I wrote in my abstract, when we were young, we were kind of forced at some point to memorize this multiplication table and to be able to do it quickly and so on. And maybe because we were doing it so quickly, we might have not noticed some really interesting things that are hiding inside of there. And so that's my goal for today, is to talk about them. Before I begin, I want to acknowledge that, mathematics has always been a collective community team effort for me. And so I would like to say that everything that I'm going to talk about today, I have had the joy to learn with these wonderful people, my students in San Francisco State University, my students in Colombia, my community of collaborators all over the world. And so I want to thank them because it's been a really fun journey to learn some of these things with them. So let's begin with something that seems very simple, multiplication. I should say that let me invite you that hopefully somewhere near you at home, you can find some paper, you can find a pencil, because throughout the talk, even though it'll be a little bit challenging to some audience participation, I won't know exactly what you're doing, but I still would like to ask you some questions and to share some of your answers in the comments. So let me begin with a question that I would like to ask you. And the question is, how do you compute 2 times 3 times 4 times 5? Okay. So I would like to ask you, 1, what answer did you get? 2, how did you get that answer? And 3, how did you feel doing that? That might be an unusual question, but I would like to ask you to calculate 2 times 3 times 4 times 5, and then tell us what answer you got and how you did it. And maybe I'll give you a minute to type your answers. And let me say that I care about question number 1. I care about your I care about your answer to question 1. I care more about your answer to question 2, and I care even more about your answer to question 3. So please try to answer all of them. And I put a little pin here that says "Talk to your neighbor" that I got from the Life is Living Festival in Oakland. If you happen to have somebody next to you that's watching with you, I would love for you to talk to that person about how do you do this computation. So far I see a couple of answers. Let me wait for a few more. And maybe before we get to the numbers, I want to acknowledge, for example, the comment from Eric Waters. I felt a bit hesitant. It's interesting because I think I'm talking largely to mathematicians, and maybe mathematicians are excited by a question like this. But this is a question that I like to ask out and about, and it is interesting how I think many people will tense up and will get nervous when you ask them a multiplication question, because we associate it with this kind of testing where, like, you were asked a question, but you're also supposed to get there really fast and get there really right. And you know, I do think that sometimes a simple question can produce some anxiety, which is not what we want to do. So okay, let me read some of the answers. So for example, actually, I'm going to switch to my other screen so I can draw some of these things. So I am looking at the answer from Mon Cordero, who says that they did first 5 times 2 is equal to 10, then 3 times 4, which is equal to 12, and then they multiplied it and got 120. So I like this process because by rearranging some of the numbers, Mont was able to get a 10 here, and somehow we know that it's easier to multiply than 10 than to multiply by 3. So that was a nice trick. So another way that I'm seeing is from somebody called XYZ DCP, who first did 2 times 3 is 6. Then they did 4 times 5, which is 20. And then they multiplied those and they got 120. Then I have a question. I have a process from Joseph Fazio, who did 2 times 3, which is 6. And then Joseph multiplied by 4. So they got 24. And then multiplied by 5. And they got 120. It looks like Mark did the same thing as Mont. It looks like Joanne might have done the same thing as XYZ DCP. Deborah Sheldon recognizes as 5 factorial. So maybe you knew already that the answer was 120. There's another process by Bernd who's saying 2 times 3 is 6. And then it looks like Bernd decided not to multiply by 4, but to multiply by 5 so that they could get a 30 and then multiply that to get 120. Yeah, I mean, pressure to answer fast, a little anxious that maybe the answer is wrong and you're saying it in front of the whole internet. I thank you all for your help and your participation, and it looks like all of us got the answer 120. That's the answer that I got also. But more interesting than the answer to me is the fact that we just had these very different processes that gave the same answer. And so if we could go back to my other slides, I would like to point out this thing, which is that different processes give the same answer. If I could see your faces, I would ask you to raise your hands to ask you who is surprised by this and who is not surprised by this. And usually when I ask people, they're not surprised, but I'm always very surprised by this. Even though I've been doing mathematics for so long, I think that there's some magic happening and that there's some beauty that we're doing these different processes, and each one of these processes is somehow giving the same answer. And so this is really what I would like to talk about today. Why do we get the same answer? That's the topic of today's lecture. Okay. So you might know 2 simple laws that have complicated names that are the reason that we get the same answer. When I ask people what, especially when I ask a group of mathematicians why we get the same answer, they say these long words, commutative and associative. So the commutative law says that A times B equals B times A. So it doesn't really matter which number you put on the left and which one on the right. And the associative law says that if you want to multiply 3 numbers, A, B, and C, you're going to get the same answer if you first do the 2 on the left and then multiply that by the right, or if you first do the 2 on the right and multiply that by the left. And these are things that we are used to by now, and we think that they are very usual, but they're kind of wonderful in some way. And sometimes this is summarized as saying that the order of operations doesn't affect the result. So we can kind of move around and do that multiplication in whatever order we want. And no matter what, if we are very careful, we're always going to get 120 for that product. So order doesn't matter. So why is it that order doesn't matter? Let's talk about this. So this is the commutative law. A times B equals B times A. Why is that? It's interesting when I teach my introduction to proofs class, I will ask students this question, and often the first answer is, well, that's the law. I was taught this, and this is one of the laws of mathematics. But it's good to keep thinking, okay, but why is that really? And one illustration that we can give for this law that I think makes it intuitive is the idea that 2 times 3 is supposed to do 2 3s, and 3 times 2 is supposed to be doing 3 2s. And then the idea is that if you do 2 columns of 3, you get this rectangle like this, and that's going to give you the same answer as if you just flip the rectangle and instead you do 3 columns of 2. Okay, so this is one illustration for why this is true. And so, is this a proof? Is this a proof of the commutative law? Well, it's not to a mathematician, and it's not to a mathematician because we have never seen anybody do this, for example, for the numbers 202 and 117, and we would not want to do it either. Draw a 202 by 117 rectangle and count those little squares and then flip it and then count them in the other way. We assume that it's still going to look the same way, but somehow we don't have proof that that's what's going to happen, and mathematicians would consider that an illustration, maybe a convincing illustration, but not a proof. And mathematicians tend to say, okay, let's think more slowly about why is it that A times B equals B times A. If you ask one of the world's fastest mathematicians why A times B equals B times A, this is the answer that he would give you. So this is Terry Tao's book, Analysis 1. And in about page, I forget which page, but I'm showing at least 16 pages. So after many pages of hard work, he goes on to prove the following lemma. Multiplication is commutative. Let n and n be natural numbers, then n times n equals n times n. Actually, he doesn't prove it. He leaves it as a homework to the reader to do it. So to explain what is going on here, what Terry Tao is doing in this book, and different mathematicians will do this in different ways, is that they will say, okay, what are the foundations of mathematics? What are the foundations of the number system? What are the foundations of the natural numbers? And they will begin with some axioms. And in the case of this textbook, he's using Peano's axioms. And actually, A times B equals B times A is not one of the axioms. You need to prove it. And so what you need to do is start with the very careful axioms that are laid out, and from there, prove that A times B equals B times A. And this is the kind of thing that some of us find fun if we like playing with this kind of thing. I think some of us might find that this is just like a lot of work for something that might not seem worthwhile. But I think I would like to make the point, and I think again, even though Terry Tao is one of the fastest mathematicians, I think he would agree with me that sometimes it is very useful to take things slowly, even if you can go fast. We learn a lot from thinking slowly about what we think we understand. 2 ways that I would say that is, one is that we are able to build solid foundations for our theories. And it's a very interesting topic. Like, the topic of foundations of mathematics is a very interesting, deep topic with a lot of surprises, and it's very important to build carefully. And any house can topple over if your foundations are not strong. So it's good to build solid foundations. But the other thing is that if you move slowly, you are often able to discover really cool things that you missed the first time that you did it and you went too fast. So now I would like to ask you to take out your piece of paper and let's think about the following question. Why is 2 times 3 times 4 times 5 the same as 5 times 2 times 4 times 3? Or put it differently, or putting it more generally, why is ABCD equal to DACB? And one thing that I would like to point out is that the commutative law, which Terry Tao proved in the previous page, is a commutative law for products of 2 things, but now we're looking at a product of 4 things. And so what I'm asking is whether you are able to write down a proof for why ABCD is equal to DACB, just very carefully using only the commutative law, which tells you can exchange two things, but it doesn't tell you that you can exchange all four things in any order that you want. So I'll give you a minute to think about. And if you have a proof, feel free to write it in the chat. Why is ABCD equal to DACB using only the commutative law that AB equals BA or XY equals YX? And maybe while you're thinking about this, if you don't want me to spoil the surprise, feel free to mute me for a moment while you keep thinking. And maybe I'll talk us through how I might go about doing this. So, okay, I have A, B, C, D from left to right, and I want to get them in the order D, A, C, B. And the commutative law tells me that I can swap the order of two of the factors, okay? And so I'm thinking what I'm going to do is that D is all the way to the right, and I want to get it all the way to the left. And so what I'm going to do is say, okay, first A, B, C, D, because I want to move D towards the left. Let me say A, B, C, D is equal to A, B, D, C, right? Because C, D is equal to D, C. So in the first step, I swap the order of C and D. And now I want to keep moving that D further to the left. So let me switch the D with the B. So then, because BD is equal to DB, that means that I can say that these things are equal. And now I want to get D to the first position. So let me swap the A and the D. So AD is equal to DA, so that allows me to do this. And now let's see, I wanted to get to DACB. I want DABC, so I'm really close. All I have to do is say, well, actually, that last BC is equal to DACB, because BC is equal to CB. And so I get this proof that ABCD is equal to DACB. And it looks like Mont gave us a similar proof. It looks like it's a little bit different from mine, and I think that's great. And it looks like Mont made a typo the same way that I made a typo the first time that I made this slide, and then I had to fix it. And I think probably some other people who are watching have different proofs. But this is one possible proof that ABCD is equal to DACB. Okay, so this begins to tell us why it may be that rearranging the numbers from left to right is not going to change the result. Okay, and that's fine. But what about all the other orders of A, B, C, D? If you look at the different answers that people gave, there were 4 different orders, and in fact, because there are 4 things, I have actually 24 different orders of A, B, C, and D. There are 24 possible expressions for multiplying A, B, C, D. Forgetting parentheses for a moment. And so I want to ask, why do they all give the same answer? Not just these 2, but any of them, okay? So let's think about this. And so now let me ask you a question and give you a minute to think about this. So again, let's forget about parentheses for a moment and just look at the left to right order of the variables. And so the first question that I would like to ask you is, so we're going to do the product of 3 things, A, B, and C. And so I am asking you, what are all the possible orders for multiplying A, B, and C? And why do they all give the same answer? Can you prove it? Okay. So I'm going to give you a minute to write down what are all the possible orders left to right that you can organize A, B, and C. And why are they all giving the exact same result? And maybe while you do that, I'll make a comment to 2 of the comments from XYZ DCP and from Sheldon Axler that are telling me, you probably should be thinking about the parentheses, because actually we are also using associativity here. And I agree, and I am putting that on hold for a moment, and in about maybe 10 or 15 minutes, we are going to talk about associativity and how we're using it. But for a moment, let's imagine that the parentheses don't matter, and we're just looking at the left to right order of the variables. Okay? So, okay, so maybe what I will do is while you're still writing the possible orders for multiplying A, B, and C, let me go to my other slide and write some things down. Okay. So what I got is that there are 6 possible orders for A, B, and C. And one way that you could do it is to kind of write them and keep looking for them until you think that you're done. The thing with these kinds of combinatorial problems, when you're supposed to list all the possibilities, is that it can sometimes be easy to miss some of them. And so in order not to miss them, I was very careful, and what I did is that I wrote them in alphabetical order. So I wrote first ABC, then ACB, BAC, BCA, CAB, and CBA. And those are all equal in alphabetical order. Sorry, those are all the possible orders listed in alphabetical order. And now I would like to argue that these 6 expressions are equal to each other. Okay, and just to remind ourselves, what the commutative law says is that xy is equal to yx. So you're allowed to swap 2 of them, but now the question that we're asking ourselves is, why are you allowed to swap all 3 of them? Okay, and maybe what I'll do is this. I'll say, okay, let me start with ABC. And one thing I'm going to say is I could swap the last 2, B and C, to get that ABC is equal to ACB. Okay, because BC is equal to CB. Next, I'm going to say, okay, but I can now swap these 2 and say that AC is equal to CA, and therefore ACB is equal to CAB. So those 3 things are equal to each other. Now I can say, okay, let's swap A and B. And I'm going to get that this is equal to CBA. Okay? And now again, I can swap C and B, and I'm going to get that this is equal to BCA. And then I can swap C and A to say, oh, then this is equal to BAC. And therefore, these things are all equal to each other. And that's my proof that all of these 6 products are equal to each other. Now, I don't know about you, but I'm feeling very uncomfortable right now, because each time I was kind of saying, okay, first I apply the commutative law to the right, then to the left, then to the right, then to the left, then to the right. And even though I don't have to, I want to apply to the left here. And if I apply it to the left, what I find is that BAC is equal to ABC, and that actually gives me a shorter proof that those 2 are equal, right? So if I want to prove that ABC is equal to BAC, I would rather give this short proof instead of having to go around and give this long proof. And so it's worth writing that connection also, okay? And I would say that this is a very nice kind of graphical proof that these things are equal to each other. Hey, Jewel, it's great to see you. So let's switch to the other slides for the moment. And now I am going to draw this picture again, now a little bit nicer, because I actually am very interested in this shape that came up. And I would like to call this the shape of 3 commutativity, okay? So if I want to understand why 3 things commute, I would like to say, well, I just wrote these things down, and I wrote what are the different exchanges that I can make. And then what I get is the shape of 3 commutativity. Okay, so that explains to us why the product of 3 things gives the same answer, but that still doesn't tell us why the product of 4 things gives us the same answer, okay? And this is going to be more complicated and still fun to do. Again, if you would like me not to spoil the fun, please feel free to look away for the next little bit. But the question that I would ask you is, now, if you have A, B, C, and D, then there's 24 different orders that you could write these things. And now I would ask you to prove that they are all equal to each other, okay? And then what you can do is you can say, okay, here's A, B, C, D. And now there's some things that you can do. For example, you can swap A and B. So that gives you that ABCD is equal to BACD. Or you could swap the middle ones, the middle two. That gives you that's equal to something else. Or you could swap the two to the left. And that tells you that that's equal to something. And then you continue and you do it like we just did with that little hexagon. But if you do it very, very carefully, you get this beautiful picture. So what you're seeing in this picture is the 24 possible orders of the letters A, B, C, and D. Those are the little pink things. There's 24 of them. And then you're seeing a blue edge between them whenever you can get from one to the other by a simple application of the commutative law. You just say xy equal to yx. Okay? And so because everybody is connected to everybody in this graph by a path, that means that all 24 ways of multiplying are equal to each other. But now this is where I think it gets interesting, because somehow it gets less interesting to me that those 24 things are equal to each other, because I think I already expected that, and so did you. But what's interesting to me is this picture. So what is this picture? And if you are a football player, a soccer player like me, you can kind of get the impulse to kick this thing, because this looks a little bit like these classic footballs from the World Cup 1970. Except this one is made of hexagons and pentagons. But this thing, you kind of want to wrap it around and look at it like a 3D object. And it's worth doing that. And what you get when you do that is this wonderful picture. So this is actually what we call the skeleton of a polyhedron. It's a three-dimensional polyhedron. And so really, I think I would like to say that the shape of 4 commutativity, in other words, the shape of why 4 things commute, is this wonderful 3-dimensional thing that almost looks like a soccer ball, but it's a little bit more angular. And this polytope has several names. For example, sometimes people call it the truncated octahedron. I just think it's a beautiful shape. So this is one of the main creatures of this talk. Okay, the name of this shape is the permutahedron. So what I'm showing you here is the shape of 3 commutativity is the permutahedron of dimension 2, which is the hexagon. The shape of 4 commutativity is the permutahedron of dimension 3. But why stop there? We could also do it for the shape of 5 commutativity. So if you look at the 120 ways of multiplying A, B, C, D, E, and you see how they are connected to each other by the commutative law, you can also do this in any dimension. Okay. Now, there is a way to build this as an actual solid in n-dimensional space. So Schott in 1914 did this construction, which I'm showing in 2 dimensions, but he did it in every dimension. So for example, to get this hexagon, which is the 2-dimensional permutahedron, one thing you can do is look at the 6 permutations of the numbers 1, 2, and 3. And each one of those gives you a point in 3-dimensional space. So you get 6 points in 3D space. And then you look at what is the shape that they form. If you kind of wrap a rubber band around them, what is the shape that they make? And even though this is 3-dimensional space, actually those 6 points are on a plane, which is the plane x plus y plus z equals 6. So actually they are on a slice of 3D space. It's a 2-dimensional slice. And the shape that these 6 points make is exactly this hexagon. And Schott constructed this in any dimension. Okay. So for the next dimension, for example, here's one beautiful way of constructing this 3-dimensional polytope. It's a little bit counterintuitive, but it's actually easier to construct this in 4-dimensional space. Because in 4-dimensional space, you can consider the 4 factorial, which is 24, permutations of the numbers 1, 2, 3, and 4. Each one of these permutations, 1, 3, 4, you can regard it as a point in 4-dimensional space. You look at the convex hull of those, and even though they are in 4-dimensional space, they live in a 3-dimensional slice given by the equation x plus y plus z plus w equals 10. And so you get a 3-dimensional shape, and it's this beautifully symmetric shape called the permutahedron. And this works in any number of variables and any number of dimensions. The same construction works And in particular, you could say that this gives a proof that for the commutative law for any number of factors, because if you are in n dimensions, so if you have a product of n things, then the ways of multiplying n things are the vertices of this shape, this polytope. A polytope is the name of a polygon in high dimensions. And the one skeleton of any polytope is connected, meaning that you can walk from any vertex to any other vertex through a path. And that path is going to give you a proof that those two products are equal to each other. Okay. And so this beautiful shape tells the story of commutativity. Okay, that's the permutohedron. So I really love this shape, and I want to show you that it shows up in some unexpected places. One unexpected place that it showed up is actually one wonderful thing about being a mathematician is that we get to visit our colleagues in different parts of the world to do math together. And I was visiting my colleague and friend Arnaud Padrol, who is in the Sorbonne University in Paris. And there they have this really wonderful museum of minerals that nobody ever seems to visit. It's in the basement, and it's just absolutely gorgeous. And in that museum, I found this beautiful shape, and it was a crystal of fluorite. And I was just so excited that fluorite is the shape of four commutativity. So this thing is not just a figment of Schout's imagination or a mathematical construct. It also occurs very naturally in nature. You might have seen it in a playground, and also while I was in the same visit in Paris, I was at this African music festival in La Goutte d'Or, and I was in this playground, and they had this permutahedron that I just had to climb inside. And it might be that there's some permutahedron somewhere near you. I encourage you to find it. One thing that I learned a couple of years ago when I visited the Science Museum in San Francisco, so we have this exploratorium that is wonderful. It's a very interactive museum. And there they had a bunch of these permutahedra. And what I had never noticed is that they stack into each other perfectly. In other words, you can make a perfect tiling of space where they all stack perfectly and there's no extra space left over. And in fact, this happens in any dimension. So in any dimension, the n-dimensional permutahedra actually stack perfectly to tile space. So I really love this construction. And if anybody's curious, I can tell you why that is. It's a very beautiful fact, which is actually not too hard to prove once you think about it in the right way. And in this playground in Tarragona, in Spain, they apparently knew this, and so they made this beautiful playground made of a stack of permutahedra that you and your friends can climb into. So I hope that mathematics will take me there one day, because that looks like a really fun playground to play in. I also have a friend. So during the same visit, I got to visit my friend and colleague Luca Mocci, who is a professor in Bologna in Italy. And we had a wonderful dinner, a wonderful homemade Italian dinner. And afterwards, when we were gathering, one of the friends who was a chemist was looking at this picture and was saying, this is actually like this is zeolite. And so I went to learn about zeolite. And it turns out that in chemistry, they build these things called zeolite sieves. And they're made of these permutahedra put together by various different things. And they use it as sieves in order to filter substances. So they use it at a very microscopic level to separate different gas components. And I actually learned preparing this talk that this is literally used to treat radioactive waste. So after the nuclear disaster in Fukushima in 2011, when there was all this radioactive material everywhere, one of the solutions they came up with was just to make these huge sacks of zeolite, which looks like sand, and they just threw a bunch of sacks of zeolite into the basement of some of these nuclear plants, and somehow this kind of absorbs the radioactive material. To me, this is just absolutely amazing that chemists are able to do this, because these things exist in nature, but they're also produced in labs in order to serve many purposes. So I think this is a really beautiful place for permutahedra occur. just to show you, this is what the 4-dimensional permutahedron looks like. And this is what the next one looks like, the 6-dimensional one. This is a beautiful polyhedron. It has dimension n-1. The number of vertices is n factorial. The number of walls is 2 to the n-2. And I really love this fact that the volume of this shape is n to the n-2. And I love this fact because this is a very important number in combinatorics. But I also love this fact because I don't know any proof that says any multiplicative proof. You would think if the volume of something is n times n times n times n, then maybe the answer should be, well, it's because the volume is like, this length times this length times this thing. But in fact, I don't know any multiplicative proof that explains why the volume of this thing has such a beautiful multiplicative formula. The best way that I know how to do this is to take this shape and cut it up into little unit cubes and proving that the number of little cubes is equal to that. It's a very beautiful fact. Okay, so that's what I wanted to tell you about the permutahedron. And again, the point that I wanted to make is that just by thinking of these different orders in which we multiply things, we get access to this beautiful shape that has a lot of wonderful properties. Now, let me pause for a moment, take a sip of water, and maybe take a moment to think about now what happens if we come back to thinking about the parentheses, because we ignored the parentheses for a while. We ignored the association, the grouping. So let's think about that for a moment. So the associative law, which I think has a very strange name, that's somehow, maybe you might call it the grouping law or something, because I don't see what this has to do with association so much. But in any case, it basically says that you can insert parentheses into an expression in any way, and the answer is not going to matter. What's the idea here? And I think this is what Sheldon was referring to earlier. I've never met anybody who can multiply 3 numbers in their head. I've never met anybody who can do 3 times 5 times 7 in their head. Everybody has to say, okay, let's first multiply these 2 and then the other one. So we multiply numbers 2 at a time, probably because when we were little, we were forced to learn the multiplication table, which is x times y. Nobody forced us to learn the multiplication cube, which would be like an x times y times z 3-dimensional table. So the operations that we do are binary. We multiply 2 numbers at a time. Okay, that's the basic way that multiplication works. And so we want to multiply 2 numbers at a time. So I'm giving you an example of how to compute A, B, C, D, and I'm giving you a non-example. In the first example, I do BC, then I multiply that result by A, and then I multiply that result by D. In my non-example, I'm calling it a non-example because there I first multiply B and C, but then I am left with 3 numbers and I don't know what order to multiply them in. And I want to group so that I multiply 2 at a time. Okay? The associative law says that grouping doesn't matter for 3 numbers. It doesn't matter how you group, you're going to get the same answer. But we did 2 times 3 times 4 times 5. That was 4 numbers. And so we would like to talk about why grouping doesn't matter for 4 numbers. And actually, the associative law doesn't immediately imply that we should have gotten the same answer. Okay? And so I am going to ask you a question. And again, maybe you can jot down in your piece of paper. Let's say now that we're going to multiply A, B, C, D. And we already talked about the rearranging left to right. So let's forget about that. Let's not rearrange left to right. Let's just insert parentheses so that we get 2 factors at a time. And so the question that I have is, what are all the ways of grouping the product A, B, C, D? But you only multiply 2 factors at a time. And then once you have those, think about why they all give the same answer. And can you prove it? So I'll give you a moment to think about that. And I'm going to show the answer in a moment. So again, if you would not like to see the answers, feel free to mute yourself for a moment or look away from the screen. If you don't mind a spoiler, then let's go to my other screen and look at the possible parenthesizations for A, B, C, and D. This word is so hard for me to say. Parenthesizations. Groupings, ways of putting binary parentheses. Okay, I did it very carefully, and I found that these were the only ways that I could find, and I really tried hard, and I couldn't find any others. So those are the possible parenthesizations for A, B, C, and D. Okay, there's 5 of them, and so now I would like to ask, why do they give the same answer? Okay, and so I'm going to do something similar to what I did earlier, where I'm going to say, okay, first, let me take this expression and say, look, I can apply the okay, let me write the associative law so that we don't forget what it says. The one thing that we're allowed to do is take the product of 3 things and move the parentheses from the left 2 to the right 2. Stashev used to joke and call this the perestroika option, but he didn't know if you were moving to the left or to the right. So why do these give the same answer? So I take these 3, A, B, and C, and I say, okay, I can apply the associative law, and I'm going to get that this is equal to A times BC times D, right? And now I'm going to say, okay, look, I have the product of 3 things, A, B, C, and D. So I can apply the associative law to them and move the parentheses from the left 2 to the right 2. Okay? Then I'm going to say, okay, let's forget the A for a moment and apply the associative law to these 3. So I leave the A alone, and then I shift inside the parentheses from B, C to CD. Okay. Now I have a product of 3 things, 1, 2, and 3, and I'm going to apply the associative law to them. So the parenthesis is currently around the right 2, so I'm going to put it around the left 2. So I'm going to get that this is equal to AB times CD. Okay. And that gives me my proof that those 5 expressions are all equal to each other. But again, I'm feeling unsatisfied at the moment, because when I was doing that, I was finding that every time that I was coming from one expression, I had another one to go to. And that happens here also, that I can look at this expression and say that's a product of A, B, C, and D. And I can move the parentheses away from the right 2 and to the left 2 and get to this expression. So I'm going to get that these are equal to each other. And again, the point is that to prove that this is equal to this, I can do it in one application of the associative law instead of going around 1, 2, 3, and 4 applications of the associative law. Okay? And this is going to be a question that I'm going to come back to later, which is, if you have 2 expressions, how quickly can you get from one to the other by applications of the associative law? It's a very interesting question. But in this case, these are the 5 possibilities. They're all equal to each other. And these are all possible applications of the associative law. And so I get a nice pentagon, which I'm going to call the shape of 4 associativity. So let's go back to my other slides now. And let me show you a nicer rendition of this picture. So here is the same picture that I had a moment ago. So again, the vertices are the different parenthesizations, and the edges say one is equal to another. Okay, that's the shape of 4 associativity, and I can do this in the next dimension. So now, if instead of saying I wanted the product of 4 things and all the ways that they can be grouped, I could say, what about the products of 5 things? So in this case, there are 14 different groupings, and if I do it carefully, I gave this for homework to my students in an introduction to proofs class, and they gave this very beautiful picture where each vertex is one of the groupings, and each edge shows that those 2 expressions are equal to each other. So I love this picture. It has a beautiful shape of an egg, and you can see how it's kind of three-dimensional. And sometimes people like to draw it like this to actually make it have straight faces and be a polyhedron. And it's debatable which one is nicer. I think the left one is more beautiful. The right one is a polytope, and so that's nice too. Okay, so that polytope is called the shape of 5 associativity. And this polytope is called the associahedron. So for 4 associativity, you get a pentagon. For 5 associativity, you get this other three-dimensional shape. And in that same class, I joked to my students, and professors should be very careful of the jokes that they make, because I joked and I said, oh, maybe y'all should do it for 6 associativity. So you should draw the 42 groupings and prove that they're all equal to each other, and you're going to get a 4-dimensional polytope. And actually, my student Christine Allard did it, and it gave me this very beautiful picture, which I had never seen, of what the 4-dimensional associahedron looks like. And this is when she was in her second year as a sophomore at San Francisco State. So that was very exciting. So this is a very beautiful polyhedron. It has dimension n-2. The number of vertices is known as the Catalan number, 2n factorial divided by n factorial n plus 1 factorial. The number of walls is n times n plus 1 over 2 minus 1. And one thing that is interesting to me is that I don't know a nice formula for the volume of the associahedron. There are difficult formulas, and I know some formulas, but I don't know of a beautiful formula. And it may be that it exists, or it may be that it doesn't exist. But this is not known whether there's a nice formula for this volume. The associahedron has a very interesting history. It's been discovered a few times. This quote is from a manuscript of Mark Heyman in 1984. The associahedron is a mythical polytope representing the parenthesizations of variables. It was first sketched by Tamari in 3 dimensions, and he was doing work in algebra and really studying the associative law, actually. But he was not able to prove that this was a polytope in any dimension, but he conjectured that it probably was. Stashev rediscovered this in 1963 in his PhD thesis, which was in homotopy theory in topology. So it's a very different area. And Stashev actually built an egg-shaped associahedron. So his did not have straight faces, but he did prove that topologically it was a ball. Okay. And there is this terrible story about Milnor. So Milnor was a wonderful mathematician, but he did something that I don't think is wonderful, which is that he showed up at Stashev's thesis defense with a sculpture of the 3-dimensional associahedron and told him, look, how could you not notice that this is actually a polyhedron, not just topologically a sphere, but actually can be realized as a polyhedron. And that didn't make Stashev feel great, given that he was given this wonderful defense, and Milnor kind of belittled it a little bit by having him not notice that it was a polytope. But what's interesting is that actually Milnor never wrote down a proof that it was a polytope. He just claimed that it was a polytope, and it was only in 1984 that Mark Heyman wrote the first published proof. Actually, this was not even published. This was in a manuscript, some handwritten notes where he constructed this as a polytope, which then Lodey published and gave a lot of beautiful work done. And then there's this beautiful survey of Cesar Ceballos and Paco Santos and Vincent Pilot, where they give many, many different realizations of this polytope. And this recently reappeared in physics in the work of Nimar Kani-Hamed and others. So let me just tell you a few brief stories about this. So one story about the associahedron that I like a lot is that the associahedron appears in work of Bill Thurston, joined with Tarjan and Sleater, who were working in algorithms. So they were studying efficient algorithms for binary search trees. And what they proved is that the graph of the associahedron is 2n minus 6. So that means that you can go from any vertex to any other vertex in 2n minus 6 steps. In other words, if you want to show that 2 different parenthesizations are equal to each other, you can do it in only 2n minus 6 steps. And they proved this for large enough n. And Purnin proved later that actually this started being true at n equal to 9. What I think is really remarkable is that the proof of Sleater, Darjan, and Thurston is using some hyperbolic geometry, and they basically give a bound on the diameter by computing some hyperbolic volumes in three-dimensional hyperbolic space. I actually had never seen that paper until this morning, and I'm really looking forward to studying it because I think it's really fascinating. I recently went to this conference at Harvard that was getting people who think about combinatorics and algebra and geometry to talk to people in theoretical physics. And Nimar Kani-Hamed, who's a physicist at the Institute of Advanced Studies, gave this very beautiful talk in which he was explaining that. So he has a very ambitious program to rewrite the foundations of space-time and quantum mechanics. I want to acknowledge that I'm not an expert in these things. But in talking about these foundations, he was explaining that the icosahedron plays a really important role in those foundations. I'm not an expert in this. I'm not going to pretend that I am, but I'm going to invite you to look up this talk, which is really fascinating and actually really nice to follow on how this appears in theoretical physics. And maybe the thing that I would like to conclude with is that here you can see the permutahedron and the icosahedron together. And there's a very beautiful observation of Alex Posnikov, which is that you can build the icosahedron from the permutahedron. And all you need to do is knock down some walls. So you take the shape on the left, and maybe you can see how if you knock off the seating, and if you knock off the face in the top right, and if you knock off a few other ones, you're going to get exactly the shape on the right. And so these two polytopes are very closely related to each other. And I won't really get to say too much about that. But if you would like to know more about this, I would encourage you to look at this book that actually just came out last week that Marcelo Aguiar and I wrote, called Half Monoids and Generalized Permutahedra. And in this book, we talk about the relationship between these two polytopes, some algebraic constructions, and how these polytopes actually have some very beautiful applications to old-fashioned calculus problems. But I think this would be a good place to stop. So I'll just flash over these slides and thank you for your attention.
Federico, thank you so much. That was an amazing lecture. And I feel like not only did you kind of hit two major things we try to really share at MAA is one, how there is an intersection between mathematics and art, or these beautiful patterns, but also the beauty of mathematics. I mean, this here was a prime example. I do want to leave a couple of minutes. If folks have questions, please feel free. We have just maybe time for one question for Federico in this lecture. Again, really appreciated this time. And I was going to ask if there were any kind of books or work that you have that really encompasses all of the patterns that you've been able to identify through the process. So glad that you left us with that, the publication to check out. Yeah, great.
Maybe one thing that I can mention is that I wrote a paper that I'm going to look up right now and try to find it. But it's a brief paper that I published in the notices of the AMS, telling a little bit of this story. And I realized that I didn't put it on the slides, and so I will look it up so that people can look up some of this information if they would like to look at it further.
Excellent. And we can definitely try to share that on our end as well. Great. I'm not seeing any questions, just lots of thanks for a wonderful lecture.
And I think I'm not finding it right now, but maybe what I'll do, and I don't love social media, but if anybody would like to post these links, I'll post them on my social media, and I'll post links to these papers that I mentioned.
Wonderful, and we can be sure to post that link as well on our social media. So.
Oh yeah, that's right. This is going to be a YouTube page, so I can also post them there in a moment.
Exactly. Great. Well, thank you so much, Federico, and thank you everyone for joining us. Again, we'll be back here October 18th at 7 p.m. for our next lecture. I hope everyone has a great day.
Thank you so much, Kira. Thank you, everybody.
Thank you.